Now, the last thing for today is I promised you an example which was not an area example. I want to be able to show you that integrals can be interpreted as cumulative sums. Integrals as cumulative sums. So this is just an example, so here's the way it goes. So we're going to consider a function f. We're going to consider a variable t, which is time in years, and we'll consider a function f of t, which is in dollars per year. All right, this is a financial example here. That's the unit here, dollars per year. And this is going to be a borrowing rate. Now, the reason why I want to put units in here is to show you that there's a good reason for this strange dx, which we append on these integrals, this notation. It allows us to change variables, it allows us to be consistent with units, and allows us to develop meaningful formulas which are consistent across the board. And so I want to emphasize the units in this when I set up this modeling problem here. Now, you're borrowing money, let's say, every day, all right? So that means delta t is 1 over 365. That's almost 1 over infinity from the point of view of various purposes. All right, so this is how much you're borrowing. In each time increment you're borrowing. And let's say that you borrow, your rate varies over the year. I mean, sometimes you need more money, sometimes you need less. Certainly any business would be that way. And so here you are, you've got your money, and you're borrowing it, but the rate is varying. And so how much did you borrow? Well, in day 45, which corresponds to t over 40, is 45 over 365, you borrowed the following amount. Here was your borrowing rate times this quantity. So dollars per year, and so this is, if you like, so I want to emphasize the scaling that comes about here. You have dollars per year, and this is this number of years. So that comes out to be in dollars, this final amount. This is the amount that you actually borrow. So you borrow this amount. And now, if I want to add up how much you get, you've borrowed in the entire year, that's this sum, I equals 1 to 365 of f of, well, it's I over 365 times this delta t, which I'll just leave as delta t here. This is total amount borrowed. Now, this is kind of a messy sum. In fact, your bank probably will keep track of it, and they know how to do that. But when we're modeling things with strategies, trading strategies, of course, you're really some kind of financial engineer, and you want to cleverly optimize how much you borrow and how much you spend and how much you invest. This is going to be very, very similar to the integral from 0 to 1 of f of t dt. At the scale of 1 over 35, it's probably, go to 365, it's probably enough for many purposes. Now, however, there's another thing that you would want to model which is equally important. This is how much you borrowed, but there's also how much you owe the bank. at the end of the year. And the amount that you owe the bank at the end of the year, I'm going to do it in a fancy way. It's the interest, we'll say, is compounded continuously. So the interest rate, if you start out with P as your principal, then after time T, you owe, so borrow P, after time T, you owe P times e to the RT, where R is your interest rate, say 0.05 per year. Okay? That would be an example of an interest rate. And so, if you want to understand how much money you actually owe at the end of the year, at the end of the year, what you owe is, well, you borrowed these amounts here. But now you owe more at the end of the year. You owe e to the power r times the amount of time left in the year. So the amount of time left in the year is 1 minus I over 365, or 365 minus I days left. So this is 1 minus I over 365. And this is what you have to add up to see how much you owe. And that is essentially the integral from 0 to 1. The delta t comes out, and you have here e to the r times 1 minus t. So the t is replacing this I over 365, f of t dt. And so when you start computing and thinking about what's the right strategy, you're faced with integrals of this type. All right? So that's just an example, and see you next time.